Hi everyone, I'm Ugne from Durham University, and in this talk I will present to you our ongoing analysis of rotation curves of high redshift galaxies, and in particular their decomposition into the baryonic and dark matter components. This work is done together with Mark Swinbank and Anna Puglisi from Durham University, as well as the rest of the curves team. Why are we interested in rotation curves? Well, in the 1970s, most famously Rubin and Ford, and many studies since then, have shown that the enclosed dynamical mass of local galaxies continues to rise far beyond the optical radius. So for example, here on the bottom left is a nice local spiral galaxy with its rotation curve on the right. And we can see that the stellar component, even when we take the gas contribution into account, cannot explain this high and flat rotation curve that we see in this galaxy. So there must be a dominant dark matter component. Since then, galaxy rotation curves have become one of the fundamental pillars of the dark matter paradigm. Even though studies of local galaxies were possible in the last century, only recently advances in near-infrared spectroscopy made these studies possible at high redshift. We are interested in high redshift because that was the peak epoch of star formation when most stars that we see in today's massive galaxies were formed, and the conditions were very different to local universe. Some recent studies report decline of rotation curves at large radii for a significant amount of their sample sources at high redshift. This is an interesting and intriguing result. So here at the bottom, I'm showing three examples from one of these recent studies. On the left, we see a nice flat rotation curve, just like you would expect from local examples. In the middle, there might be some indication of a decline in this rotation curve, and on the right is a strongly declining rotation curve. So are these more turbulent systems? Do they have different dark matter fractions as suggested by these recent studies? Well, to really assess these questions in detail, we first need better constraints in the outer regions of the rotation curves, where the constraints at the moment are the weakest. So we need much longer integration times to probe these regions in detail. And that is where the KMOS Ultra Deep Rotational Velocity Survey comes in. So it's a KMOS large program targeting around 50 star-forming galaxies at redshift 1.5. These are main sequence galaxies with stellar masses of around 10 to the 10 solar masses. The sample is split into two fields, CDFS and COSMOS. CDFS field is now complete, and we expect COSMOS observations to be completed by the end of this year. Each galaxy in the sample has around 100 hours of integration time, which is around 10 times deeper than typical surveys at this redshift. So we are expecting to probe outer regions in quite a bit of detail. And here on the right, I'm showing four examples from the field that was completed recently. And on the left column are the HST color images of these sources. In the middle are the H-alpha velocity fields, and on the right are extracted rotation curves. We can see that the rotation curves reach about 10 kiloparsecs, with some extending out to 15 kiloparsecs. And most of our rotation curves show either flat or increasing rotation curves, just like the first three rows. However, a small amount of our sample galaxies do show a slight indication of this decline, like the bottom panel. So to better visualize the whole sample of our galaxies, here are all the rotation curves of our sample galaxies overlaid together. The x-axis is normalized by the disk scale radius, and the y-axis, the velocity, is normalized by velocity at 3 times the disk scale radius. And we can see that most of the rotation curves extend to at least 3 to 4 disk scale radius, with some extending to even to 6 times the disk scale radius, as shown by these solid lines. And we can see that there's a wide range of velocities, and only a small fraction of our sample galaxies actually show this decline. So to better probe the components contributing to these velocity curves, we need to decompose them into the baryonic and dark matter components. And usually this is done by modeling the stellar and gas distributions. However, Our sources are in Candle's region, which has deep HST imaging available. So instead of modeling the stellar distributions, we can construct resolved stellar mass maps. For each of the pixels in each of the sources, we fit 10 HST bands with an SED fit encode to derive stellar mass at that pixel. And this way, we construct these resolved stellar mass maps for our sources, just like the ones seen here. Now, HST observations are taken at 0.2 arcsecond seeing, while H alpha observations using KMOS were done at around 0.7 arcsecond seeing. So to really compare these components directly, we need to smooth our stellar mass maps to the KMOS seeing. To do this, we first extend the stellar mass maps by including the best fit Cersec model in the outskirts and then smoothing it to 0.7 arcsecond seeing. At this point, then we can compare the radial profile of the visible mass to the dynamical mass that we extract from the H alpha rotation curves that have been corrected for the asymmetric drift. So here on the right, I'm showing the total mass versus radius in one of these sample sources, where orange shows the dynamical mass and the gray shows the baryonic mass. Now, to get the baryonic mass, we also have to include gas contribution in these galaxies. So to do this, we don't have, unfortunately, yet CEO maps, so we have to model the gas distribution. We allow the gas fraction to vary between 30 and 50%, and we assume that the radial extent of the gaseous component is the same to the stellar extent and allow this to vary up to 2 times the stellar extent. And this gives us the gray uncertainty region to see if the gaseous contribution was between these parameters, what the total mass from the visible component would look like. And this is still work in progress, but we can see that for this galaxy that is shown on the right, that dark matter component is the dominant component. We find this by assessing the dynamical mass and baryonic mass, and of course what's left over is the dark matter mass. And we can see that the fraction of dark matter in this galaxy is around 0.8, 0.9, even at small radius of 3 to 5 kiloparsecs. So again, to visualize these better, here I'm showing the fraction of dark matter against the radius that is normalized by the disk scale radius again. And for this plot, I'm only showing those galaxies that have V over sigma above 2, so those that are more rotationally dominated, and as well as those that don't have disturbed sigma profiles. So what we can see from this plot is our sample galaxies have quite high dark matter fractions. So for example, at 4 times the disk scale radius, these sources are consistent with a single value of dark matter fraction of around 0.7 within 2 sigma variation, which is in broad agreement to what we see in Eagle simulations or local galaxies. But of course, this is still work in progress. So even though we're using state-of-the-art facilities, there are still, of course, improvements to be done on these rotation curves and in each individual component. So ERIS will allow us to look at the inner H alpha kinematics and directly compare H alpha to the stellar component, as both observations will be at around 0.2 arcsecond seeing. JWST has a GTO-approved program in the Candles region, which will allow us to update the stellar mass maps by including longer wavelength measurements. And of course, ALMA will allow us to get the CO maps, which will be beneficial to improve the constraint on the baryonic component. So in summary, over 50 years ago, galaxy rotation curves revealed the need for dark matter in local galaxies. And with this study, we tried to assess what is the dark matter fraction in high redshift galaxies. Our preliminary results of Our sample shows that majority of Curve's galaxies show flat or rising rotation curves, and the preliminary analysis on the decomposition of rotation curves indicates high dark matter fractions that increase with radius for all of our sample galaxies. Thank you.